Hello, my name is Eric Rotenberg, and this is joint work with Vinesh, Srinivasan, and Rangeen, Basu, Chowdhury. And I'm going to present our paper, Slipstream Processors Revisited, Exploiting Branch Sets. So single-thread performance is primarily limited by delinquent branches and loads. These are branches that frequently mispredict and loads that frequently miss in the last level cache. Now, individually, these are bad instructions, but they're even worse when they coincide. By that, I mean a cache missed load that feeds a mispredicted branch. So a large window processor, which is otherwise able to tolerate long latency loads, loses latency tolerance in this particular case because we squash many instructions after the cache missed load. The graph shown on this slide shows instructions per cycle of an aggressive 4-wide fetch/retire core that has a peak IPC of 4 instructions per cycle. And as you can see on these difficult workloads, that core struggles to achieve even 2 IPC, whereas if we have perfect branch and data cache, we get much closer to the peak performance. One solution to the delinquent branch and load problem is pre-execution via helper threads. So the idea of a helper thread is to resolve hard-to-predict branches and initiate delinquent loads before the same instructions are fetched by the main thread. And there are primarily 2 classes of pre-execution in the literature. Per dynamic instance helper threads, where each helper thread is the backward slice of instructions leading to a single dynamic instance of a branch or load. And the second class, 2 redundant threads in a leader-follower arrangement. Here, the leader thread is speculatively reduced by pruning instructions. The objective of this paper is to design a new pre-execution microarchitecture that meets 4 criteria. First, we have a preference for the leader-follower style of pre-execution because it avoids tricky issues of per dynamic instance helper threads. Namely, we don't have to deal with the issue of the timing of forking and accounting for live-in values of the little helper threads. And the reason is that the leader is continuously executing in its lead of the follower. Moreover, because there's a one-to-one correspondence between control flow in the leader and in the follower threads, lining up pre-executed branch outcomes with corresponding instances in the main thread is not difficult, whereas for per dynamic instance helper threads, it can be tricky. Second, we would like to be fully automated using only hardware. Now, we're not opposed to compiler support, but requiring a compiler adds a software and hardware codependency that introduces risk. We also would like a solution that targets both branches and loads because we want a unified solution for performance degrading instructions. And finally, we'd like to overcome performance limitations of other leader-follower microarchitectures that I will be discussing in this talk. So our paper includes a detailed related work analysis, and it's summarized in this table. And the only other hardware-only leader-follower architectures in the past were Slipstream processors and dual-core execution. Now, Slipstream primarily targets branches, and dual-core execution primarily targets loads, and we like a unified solution. Moreover, even within their techniques, they do have some limitations that I will be discussing. So here's a high-level overview of the Slipstream processor microarchitecture. The leading thread is called the advanced stream or A stream, and the trailing thread is called the redundant stream or R stream. And we'll be using this terminology in our technique as well. There are 3 new components that are added to this dual core system to facilitate Slipstream execution. The first 2 components, the IR detector and IR predictor, or instruction removal detector and instruction removal predictor, are responsible for removing or pruning instructions from the A stream. And the A stream pushes all of its executed branch outcomes and value outcomes onto a FIFO delay buffer for consumption by the R stream. Now, Slipstream's removal criteria is to remove the backward slices of confident branches in the A stream in order to pre-execute unconfident branches. Now, this is ineffective for phases that are dominated by hard to predict branches when branch pre-execution is most needed, and we will see this in the results. You simply do not get sufficient instruction removal in the A stream if all of your branches are difficult. Moreover, the A stream is not really designed for low latency tolerance, and To highlight that fact, backward slice removal stemming from covenant branches do not stop short at delinquent loads, failing to convert these removed loads into non-binding prefetches. Dual core execution actually addresses that deficiency in Slipstream by targeting loads explicitly. Now, in dual core execution, we do not prune instructions per se. All that we do is, when the A stream finds that there's a load that is blocking the retire stage for too many cycles, it gives up on the load and converts the load into a non-binding prefetch instruction. And then we have to silence the execution of any dependent instructions that depend on that load. So it converts cache miss loads that block A stream's retire stage to non-binding prefetches and silences execution of their dependent instructions. Now, this technique is very good at tolerating cache miss loads, except when their dependent branches are mispredicted. In that event, the branch outcomes that are sent to the R stream facilitate detecting a wayward A stream. So if there was a mispredict that depended on unresolved load, the R stream is responsible for detecting that and squashing not only itself, but also the A stream, thereby losing load latency tolerance. Moreover, DCE was not really targeted for branch pre-execution. And that can be seen if there are no delinquent loads, the two threads are redundant and there's no actual pre-execution going on. So in this paper, we introduced Slipstream Processor 2.0, where the key innovation is to remove the forward control flow slices of delinquent branches and loads. This will overcome the performance limitations of Slipstream and dual core execution, and it leads to two firsts. First, it provides a leader-follower style branch pre-execution without relying on confident instruction removal, which is targeting the deficiency of the original Slipstream. And second, we are able to tolerate cache miss loads that feed mispredicted branches, thereby addressing the deficiency of DCE. And of course, by being able to target both loads and branches, we're also in that sense better than Slipstream and DCE by being more complete. So we meet all four criteria. And an additional point is we do have a microarchitecture turbo boost feature whereby we auto enable and disable the A stream based on profitability. So let's talk about delinquent branch pre-execution, or DBP. For this, we have to understand what is the forward control flow slice of a delinquent branch. Well, at a minimum, it's the control-dependent region of the delinquent branch. There is more to it than that, and I'll be talking about that a little bit later. So this picture on the left shows a delinquent branch in block A. Its control-dependent region as two alternate paths, B and C. And that control flow eventually reconverges at block D, and we call that the reconvergent point. So how does delinquent branch pre-execution work? Well, in the A stream, the delinquent branch is converted to an unconditional branch to reconvergent point. In other words, we skip the control-dependent region of the delinquent branch in the A stream. The A stream resolves the delinquent branch's predicate by executing that predicate computation. And here's the key point, that the A stream is not slowed by a would-be misprediction of the delinquent branch. And that's because it doesn't even need to predict the branch, because it skips its control-dependent region. Now the R stream receives an accurate prediction for the delinquent branch from the A stream, as shown by this arrow here. It should be pointed out that the skipped control-dependent region may itself have branches nested within it, and the R stream is responsible for predicting and resolving those branches on its own. So it locally predicts and resolves any branches nested within the skipped CD region. And here's a key point again, that the A stream is insulated from any mispredictions of that R stream locally resolved control flow. Now I'm going to take that same picture and put it inside of a loop to demonstrate that, delinquent branches are delinquent, not only because they're hard to predict, but because they occur a lot. And so they must be inside of a loop. And this is just to show the stream of predictions that can be supplied by the A stream now in this case, and how the R stream then, guided by those predictions, accurately fetches the right path. So here the A stream is unrolling the loop into instances A and D, and A prime and D prime for the second iteration. And same thing with the R stream. And the R stream, guided by the A stream, fetches the correct path perfectly. Of course, it has to resolve any control flow within the control-dependent regions that were skipped, and the A stream, again, is insulated from any problems that are in those regions. Now, the forward control flow slice may include some additional stuff, namely other branches that are control independent and data dependent, or CIDD, with respect to the delinquent branch and their control dependent regions. Those are also in the forward control flow slice. Let me show that with a picture. So here we have another delinquent branch. In its control dependent region, we have a possible production of R2. Now, after the reconversion point, D, there's another branch that depends on R2. Now, this branch won't be able to successfully execute because because of the delinquent branch skipping its control dependent region. So this is a CIDD branch, and this is a branch that cannot safely execute in the A stream. So we will fetch it, but not execute it, and we'll also skip its control dependent region. You'll also notice that its control dependent region has a possible right to register R3, which this third branch depends on. And so this is also control independent and data dependent with respect to the delinquent branch, but transitively via the other CIDD branch. And so how is this handled in the A stream? Well, the delinquent branch is going to be executed and its control dependent region will be skipped. But the second branch cannot be executed because it depends on something that was removed by the first branch. And so it is fetched but not executed, and its control dependent region is skipped. And likewise for the third branch. Now, we have to have an encoding scheme for sending outcomes to the R stream so that the R stream knows what to do. And the branch encodings that are supplied by the A stream to the R stream consists of 3 bits per branch. The first bit is whether or not the branch was executed by the A stream. The second bit indicates the outcome if that branch was executed. And the X here refers to whether it was taken or not taken. And then the third bit indicates whether the control dependent region of the branch was skipped or not. And with these 3 pieces of information, the R stream knows how to handle its own situation. So the first branch is encoded. So there are 3 different types of branches then. The first is a normally executed branch in the A stream, where it was executed, we have an outcome for it, and its CD region was not skipped. Then we have pre-executed branches for delinquent branches that want pre-execution. These are also executed. We also have an outcome for them. However, we skip the control dependent region in order to achieve the pre-execution effect. And then there are the CIDD branches where we couldn't execute them, so we don't have an outcome, and the control dependent region is also skipped. And so the first branch has the 1x1 encoding for executed, we have an outcome, and we skipped its CD region, and that has to be filled in by the R stream. And then these CIDD branches have the 0-1 encoding, indicating not executed, don't have an outcome, and we skip the control dependent region. So for that reason, we don't have a prediction, and the R stream has to predict and resolve the control flow itself. Now, I want to point out an interesting problem, and that is a delinquent branch is pre-executable only if it is not in its own forward control flow slice, i.e. only if it's not self-dependent. So on the left, I show the same pre-executable branch that we were showing earlier, where we unroll the loop and we can just stream these predictions of multiple instances of this same static branch. Here, I take the same loop, but I add a twist, which is we have a right to logical register R1 within the control dependent region of the branch. Well, the branch itself does depend on R1, and so future instances depend on previous instances. And so this is not a pre-executable delinquent branch. And that can be seen here, where maybe the first instance is pre-executable, but since we skip the control dependent region of the first instance, the second instance has to be silenced and we don't have an outcome for it. And same for all subsequent instances. So this is not a pre-executable branch. So now I want to define branch sets. Well, in a sense, we already defined it. So the branch set of a delinquent branch or load are the CIDD branches with respect to the branch or load. And the concept of branch sets is important for two reasons. First, that the branch set constitutes the forward control flow slice that needs to be removed. And second, it's a litmus test for whether a branch is pre-executable or not. A delinquent branch is pre-executable if it is not in its own branch set. Now let's move on to delinquent load prefetching, or DLP. So here's a load in block A. It's a delinquent load, so it misses a lot in the last level cache. It writes to it loads a value from memory into R1, and this branch is in the loads branch set because it depends on the load through R1. Here's how DLP works. In the A stream, the delinquent load is converted to a non-binding prefetch, as shown here. Now, that prefetch is likely to miss in the level 2 cache, and that's sort of the point. It's going to initiate a prefetch early. Any branches in its branch set have to be silenced and the control-dependent regions skipped, as shown here. So they get the 0-1 encoding in the delay buffer. Now in the R stream, the delinquent load will execute like normal, and hopefully it'll hit in that level 2 cache. Now, it also understands that this branch has not been resolved in the A stream, and so it's going to have to locally predict and resolve that branch. And here's the key thing: the A stream is insulated from any R stream local mispredictions in the load's forward control flow slice. In short, we can tolerate this load missing even if the branch that depends on it is mispredicted. And the reason is we removed that branch and its control-dependent region from the A stream, and we're insulated from any bad effects of that branch. The R stream will resolve any mispredicts itself without affecting the A stream. So we can tolerate cache missed loads feeding mispredicted branches. Here's the Slipstream 2.0 microarchitecture, which looks at a top level, it follows the same template as Slipstream 1.0, but the three components, delay buffer, IR detector, and IR predictor, are implemented differently. So we already talked about how the delay buffer has a 3-bit branch encoding to cover the 3 different types of branches. The IR predictor has entries for the 3 different types of things that we need to keep track of. The branches that are targeted for DBP, the loads that are targeted for DLP, and any branches that are in the branch sets of the DBP branches and DLP loads. These are the CIDD branches. And it's the instruction removal detector, or IR detector's job, to identify delinquent loads and branches, identify reconvergent PCs of branches, and perform branch set analysis. In our implementation in the paper, these 3 components take up 4.2 kilobytes of storage. So here's Slipstream 2.0's IR detector. We have a piece of machinery that's borrowed from past work, Collins et al., automatically detecting reconvergent points. This is always going on in the background. We have the branch load classifier, which over an epoch of 500K cycles monitors how many mispredictions and how many misses each of the loads and branches in that epoch encounter. And at the end of that epoch, we have an idea of the top 8 delinquent loads and branches. And we then pass on the information for those top 8 delinquent load and branches to the branch set analysis. And what we supply to it are the program counter of the delinquent branch or load and its reconvergent PC if it's a branch. And what branch set analysis does is it trains a branch set of a single load or branch at a time to keep things simple. And let's look at a delinquent branch, for example. The way branch set analysis works is when we see the delinquent branch, we will clear these 64 poison bits, 1 poison bit for each logical register defined in the ISA. And then for all the control-dependent instructions that follow that branch, we're going to poison their destination registers by setting their poison bits. After the reconvergent point, we're going to propagate poison bits from source registers to destination registers within the control-independent region. And then if we reach a control-independent branch that ends up being poisoned, its source operands are poisoned, we know that's a CIDD branch that has to be added to the branch set. Moreover, we will even poison their control-dependent region, the destination registers in their control-dependent region, and so on and so forth. Now, we're going to do this over multiple instances of the branch or load so that we're confident that we have a complete branch set for that branch or load. And once we do, we're going to update the IR predictor with that branch or load and its branch set. So now let's talk about results. This graph is showing IPC normalized to the baseline single core. And we show the speed up of Slipstream 1.0, the speed up of Slipstream 2.0 with delinquent branch pre-execution only, DBP. Slipstream dual core execution is next. Then Slipstream 2.0 with delinquent load prefetching only. And then full-blown Slipstream 2.0 with both DBP and DLP. So let's begin by comparing DBP, the orange bar, against the original Slipstream targeting branch pre-execution. Okay, and you can see that we're much more effective at branch pre-execution than Slipstream 1.0 in these 4 benchmarks here. So these 4 benchmarks do have quite a bit of delinquent branches, and we're much more effective at pre-executing them, thereby achieving our goal. You will notice, however, that Slipstream 1.0 does do better than DBP in these 3 benchmarks. And the reason for that is these 3 benchmarks don't have a lot of DBP potential. And Slipstream 1.0 does have some prefetching effect, even though it's not intended, it's not intentional. Next, let's compare the green bar, dual core execution, against the 4th bar, DLP. So these are trying to get prefetching effects. You will notice that across the board, except for libquantum and LBM, in these 2 benchmarks, we're just a little bit below DCE. Other than that, we're either equal, like an Omnet PP, or noticeably better than dual core execution. And in particular, if you look at BZIP2, MCF, and B waves, we're significantly better than dual core execution. So there's lots of load latency tolerance potential, but you need to be able to tolerate cache miss loads that feed mispredicted branches. Finally, let's look at DBP and DLP combined. And you will notice that in BZIP, Hammer, and A*, these are good examples where either DBP or DLP provide advantage. Okay, and then the 2 together provide even more advantage. Now that's not the only reason that you want to have both DBP and DLP. The other reason, of course, is that DBP will help benchmarks that need it, and DLP will help benchmarks that need it. But this is just showing the combined effect is sometimes greater than the whole. Summarizing performance, Slipstream 2.0 gives a geometric mean speedup of 67% with respect to the baseline, 60% with respect to Slipstream 1.0, and 12% with respect to DCE. And with respect to DCE, it can give significant performance boost due to this cache misload feeding mispredict problem. Okay, and in the interest of time, I'll just conclude my talk here. Thank you for watching, and I look forward to questions.